I'm Yumei Wang with the Oregon Department of Geology and Mineral Industries. I work for the state and we'll be talking about Part 2, Earthquake Risk Management. Now in Part 1 we talked about earthquake hazards. Here we're talking about risk and risk reduction. And risk is a combination of hazards, the vulnerability of the exposure, and also the consequence of the damage. So if you're in an area of high hazard, high seismic hazard, but all your buildings are built very well and able to withstand the ground shaking, then your risk is actually quite low. It's not high, even though your seismic hazard is high. So one of the things that we've done with Oregon is a study to estimate the future earthquake damage and losses. What we did here is we took the landscape, we put the expected ground shaking on top of that. Above that, we estimated how the ground would respond. Certain areas are going to shake harder than others if they're softer soils. And on top of that, we put the people in the buildings. And then shook it and estimated what would actually happen. So if a Cascadia magnitude 9 earthquake occurred, that would rupture from Northern California up to British Columbia. And the ground would shake for on the order of 5 minutes. And the strongest shaking would occur along the coast and strong shaking in the valley as well. And then the shaking levels would dissipate as you go inland. Now strong shaking and a long duration of shaking can cause a lot of problems. You can cause landslides, liquefaction, it can cause buildings to fail, and this earthquake would also cause a coastal tsunami. So in our study, we estimated that there would be over 5,000 fatalities in Oregon alone. So it doesn't count Washington State and British Columbia and Northern California, and that the amount of losses from building damage would be on the order of over $30 billion. Now, why are we concerned about weak buildings? Because when weak buildings collapse, it can actually kill a lot of people. In 1994, we had a very important building code change where the building code requires seismic design in the construction of new buildings. Before 1994, the seismic codes were absent, and therefore some of the older buildings in our state are actually dangerous and weak and subject to collapse. So lawmakers in 2001 passed laws that require schools, regardless of the age, and emergency facilities like police stations, hospitals, and fire stations to be seismically life-safe. Now we passed these important laws based on information from other earthquakes, including from experience in California. In 1933, there was a Long Beach earthquake. That earthquake caused 70 schools to collapse, and there were also over 100 schools that were damaged. So in 1933, actually, California passed laws that say school buildings need to be seismically safe. In 1971, there was an earthquake in California, magnitude 6.6. It collapsed a number of the hospitals there. And so since 1971, California has required hospitals to be seismically safe. There's another hospital, building that collapsed in that earthquake. So knowing that we have a lot of older buildings, what can we do about them? I'm going to present some information about the seismic risk management program that the Oregon University system has. They have over 1,000 buildings, and they are slowly getting the more important buildings fixed. We got $5 million of FEMA grants to Dogami and worked with the Oregon University system, and we strengthened 5 buildings on 4 of their campuses. These buildings include various construction types, including URMs, or unreinforced masonry buildings, as well as concrete and steel buildings, and they have successfully implemented a risk management program starting in 2005. So I'm going to show you quickly these buildings. This is a dorm building, a residence hall at Portland State. It was built in 1966, and the first floor is actually a weak floor and prone to collapse. So if your first floor collapses, everything above it is at risk. So what we did is employed a number of different structural fixes, including adding cross bracing on the first floor, adding concrete walls. This is the formwork going up, and here's the completed wall. We added a steel plate wall on one of the sides where there wasn't enough room to build a concrete wall. Here it is connected to the upper floor above it, but it's connected to the lower floors as well. We took a look at the rebar. The rebar wasn't welded together, so what we did is we had those welded together, and the building is much better off and won't collapse in a major earthquake. This is another building at Portland State. It's an unreinforced masonry building. It has the classic features of an unreinforced masonry building with the arch windows, and also a header course where the bricks are turned sideways. And what we did there is we replaced the roof so the roof was a sound structure, and we tied the walls to the roof so that the walls wouldn't fall out. We also tied the features on top of the roof. We anchored them down so they wouldn't fall down on the sidewalk and hurt people passing by. So here's the chimney getting braced, as well as the parapet getting braced. We wanted to make sure that the stairwells were solid and there for people to get out of the building, so we strengthened the stairwells as well. Here's a third building. It's a steel building down in Klamath Falls. What we had to do there is actually improve the foundation all the way up to the roof. So you can see the foundation work going on, as well as adding cross-bracing rods up on the second floor. And in this case, we also did non-structural seismic mitigation, where we tied the bookcases so that they wouldn't fall down, as well as the light fixtures so the overhead lights don't fall down, as well as securing the heating, ventilation, air conditioning system and piping, and also did a number of code improvements dealing with ADA improvements and fire life safety, asbestos, and lead abatement. Now, fourth building we fixed is at Oregon State University. It's what we call a lift slab building, and the slabs, the floor slabs, are not connected well to the columns, and they can actually collapse down pancake style so that there's very little space between the floors and a big life safety concern. Last building I'll show you here is one at Western Oregon University. You can see that on the right you have a soft story. This first floor is weak, and when the earthquake shakes, it will fail these columns and it will collapse the first floor. So what we did there was we added shear walls and also added some classroom space and office space to this one. So the Oregon University system has a 6-step method where they looked at the major buildings using a rapid visual screening method, prioritized those buildings with respect to other needs that they have, whether it's energy efficiency or deferred maintenance, then did engineering analyses. If it looks like it needs to be fixed, then a cost-benefit analysis before fixing it to make sure that the money is spent very wisely. They have a lot of buildings and they can't fix everything at once, so they have a long-term mitigation plan for fixing the highest risk buildings, and they integrate the financing and scheduling into that. So it's not possible to fix all of the high-risk buildings at once. It's really a balancing act of looking at the costs and the benefits. And what we would recommend to all building owners is to approach this with a risk management approach, where you consider these 5 elements of hazard identification, risk assessment, engaging your stakeholders, so whether that's for schools, parents and students and teachers and so forth, together with risk prioritization and risk management. So to summarize, we know that Oregon has a substantial earthquake risk, and there are ways that we can reduce that risk through earthquake risk management. Thank you.